Hello everyone, I'm Eric Willett, VP of Technology and Development at Functional Products. Today I'll be discussing our research into grease and the improvement in consistency grade and shear stability. So for today's talk, I'm going to get into a bit of the background, the concerns behind polymer and grease shear stability. I'll discuss about what are grease polymers, how do they work, what's our level of understanding, how do we design a set of experiments to prove or disprove that grease polymers affect mechanical stability. Then we're going to interpret results, create some high-level explanations of what's going on, and create some key points, takeaway lessons that we can use to improve and refine our grease formulations. So do polymers affect the mechanical stability of grease? Yes, but it can be. So as I said, polymers are becoming more and more important in grease formulation. With the NLGI high performance grease specification, these categories of performance are greatly improved by grease polymers. Grease polymers are used to improve low temperature fluidity for the low temperature grease specification, water resistance for the water resistant grease section. But there's also some concern that people have about grease polymers. They wonder, are those grease polymers shear stable? So this might refer to the high performance grease specification subcategory for long life grease. We rely on greases, and as we continue to rely on greases and grease polymers more, we need to make sure that polymers are not making the grease weaker. And that's the focus of today's research. So grease polymers are very specific polymers that are selected for their very strong interaction with the grease thickener network. They have very strong effects at low treat rates. So we have an orange soap thickener network, calcium stearate, aluminum complex. They can be heated and softened about 80 to 120 degrees Celsius. Then we add a polymer, we mix them together, and we cool them down. Now, if we have a grease polymer that forms some special strong interactions, we form this tightly bonded interpenetration. Three types of those strong interactions that grease polymers use to bind to and reinforce the grease thickener network. The first is temperature sensitive. So these are the polymers that have long stretches of ethylene, the waxy crystalline unit in the polymer. This waxy crystalline unit likes to associate between different polymer chains, between polymer and stearates in your thickener network, and they bind the polymer to the thickener very tightly. Hydrogen bonding is another mechanism. Instead of nonpolar ethylene crystalline interactions, we have strong polar positive negative sites, almost like a magnet, but the polymer will form hydrogen bonds between the polymer and other polymers, but it'll also associate with hydroxystearate, polarity on your sulfonates, and things like your hydroxyl groups on aluminum complex. The last category is reactive. So it actually forms a chemical change. So we have a polymer here with this anhydride functionality on the polymer. When this functionality meets a reactive lithium hydroxide or a metal soap or a hydroxyl group like hydroxystearate, it actually reacts and binds to that site, much like a diacid or a boron complex. So these are the three ways that our grease polymers can be engineered to have very specific interactions with grease that gives us very low treat. To definitively determine if the grease polymers do help or hurt mechanical stability of greases, we need to test a wide variety of greases versus a wide variety of grease polymers. We want to create as many different opportunities to see positive or negative interactions. What we're looking for, what we assume is evidence of interpenetrating network or IPN formation, is if the NLGI grade increases. So we're looking for positive increases by at least plus a half grade or more. Then what we're going to do is challenge those greases that increased in consistency. We want to test if that increased consistency is mechanically stable. Do polymers that form this IPN, assuming that it is the basis of the increased grease consistency, is that also making the grease more or less shear stable? Are grease polymers helping? Okay. So I mentioned there are three kinds of categories of grease. We're going to look at fibrous greases, which are your traditional simple lithium and lithium complex greases. So these are lithium hydroxystearate, lithium stearate. There may be a complex involved. They form bilayers. These bilayers associate into fibers, and these give you your classic fibrous grease structure. The next is the globular greases. These are calcium sulfonates, aluminum complexes. We're going to look at one of each. These, instead of forming fibers, they form globules. They form essentially soap bubbles or soap micelles. These associate and then form a globular network. So it's not so well defined as the fibrous network. Last is particle. So these are silica and bentonite clay greases. Again, we're going to look at one of each. These are formed through pyrolysis or geochemistry to generate the particles. These particles associate into aggregates, and then you form a grease network of these agglomerated aggregates. So these are the three categories of grease, and from each category we pick two different greases. So 6 greases in total. Here are the 6 greases. So these range from about an NLGI 0.5 to an NLGI 3. So we're going to add grease polymer, see if the NLGI grade goes up or down. All of these greases appear to be based on a heavy paraffinic, based on the viscosity grade and based on the viscosity index. We can't rule out that there might be some polybutene, maybe some paraffinic naphthenic blend, but generally all of these base oils look very similar. We expect them to be just heavy paraffinic greases. Dropping point data, we do not do any dropping point evaluation, but if you're curious, here's the dropping point of those greases. And then here's the inherent or the starting roll stability of the 6 greases. So after we add polymer and we see a increase or decrease in consistency, we're going to check the roll stability. Does the roll stability change versus these initial values? Now, all of these greases were milled. These are essentially commercial greases that were provided to us, but do not have grease polymer included. So these are as close as you can get to commercial greases, just we're going to add the polymer. So here are the polymers. So we know from our research going back 10, 15 years that not every type of grease polymer, the temperature sensitive polymer, the hydrogen bonding polymer, the reactive polymer, not every grease polymer works with every type of grease. They tend to be very selective. Certain grease polymers work best with certain types of greases or certain categories of grease. We also know that molecular weight is important. A low molecular weight polymer will respond a lot differently than a high molecular weight polymer. And this can also influence levels of tackiness, water resistance, shear stability. So we're going to look at 9 polymers. This is going to be a low and a high molecular weight polymer from the 3 types of grease polymers: temperature sensitive, hydrogen bonding, reactive. We're also going to look at 2 tackifiers, a high and a low molecular weight tackifier, because they do form a network of entanglement, and that can reinforce greases too. And then we're also going to include 1 dispersant PMA, or polymethacrylate. This is just, polymethacrylates and grease have kind of a long anecdotal history, and we want to do more work with PMAs and grease to see if do they have an effect or not. Okay, just some more details. So when I say low molecular weight grease polymer, these are going to be about 100,000 to 200,000 molecular weight. In terms of if you work with lube oil polymers or engine oil polymers, these are going to be about in the range of 25 to 35 SSI. For high molecular weight grease polymers, we're looking at 300,000 to 600,000 molecular weight. These are going to be, if you're familiar with engine oil, shear stability index, these would be more like 50 to 80 SSI, and the tackifier is much higher. Our low molecular weight tackifier is an olefin copolymer. Our high molecular weight tackifier is an ultra high molecular weight polyisobutylene. And our dispersant PMA has a mixture of long and short alkyl groups and 0.1% nitrogen by weight. So these are the molecular weights, and these are you're going to see differences between high and low molecular weight polymers as I show you. So with our sample preparation, we had to make about 60 greases. So that's quite a lot of greases. So the way we really accelerated the work here and created a really focused process was we first diluted each polymer at about 8 to 10 weight percent in a 100 neutral oil. So this allowed us to add these liquid concentrates to the greases very consistently. We didn't have to worry about the difficulty of mixing certain polymers into certain greases. Differences in base oils of the greases can greatly influence how quickly polymers dissolve. So pre-dissolving the polymers really accelerated and made the work more consistent. We filtered each of those concentrates, added them 95 parts base grease to 5-part polymer concentrate. We mixed the greases for 2 hours, and then we allowed the greases to rest at room temperature for 24 hours. So this is important for waxy greases and waxy polymers. They need time to form those interactions to form the interpenetrating network. Our control, so for each base grease we made a control grease, that was 95 parts base grease to 5 parts 100 neutral oil. So no polymer added. This is what we compare all of our cone penetration, all of our roll stability results to. And the last point here is we did not mill after adding the polymer. We had pre-milled base greases. We added purely dissolved polymer, very clean, without particulate. So we did not see any kind of particulate that needed to be milled. We have so many greases to interpret. We have about 60 greases, plus controls. We need to run multiple cone penetrations, many roll stabilities. It's a lot of tests to run. So what we really want to look at is trends. We don't want to get stuck looking at small fluctuations or random noise in our data. So we make 2 simplifications to accelerate the data analysis to draw these high-level conclusions that we're seeking. The first is that we're only going to consider changes in the consistency to be significant if the grease has gone up by plus or minus a half NLGI grade. So if a grade is NLGI number 2 and it stays number 2, then we don't consider that to have formed an interpenetrating network or any type of interesting grease-polymer interaction. And that is a result that is tabulated, but we don't do any further work. On the greases that showed increase in increases in cone penetration, we ran roll stability. Now, we only consider the roll stability changes to be significant if they are greater than the error that is defined by the D1831 method. So for us, it is 3.8% error or less than that, and we don't consider it to be an improvement or decrease. 3 main categories of changes to consistency. In about half of cases, there is a half or full NLGI grade increase. Almost half of cases show no change, so no evidence of IPN formation or grease and polymer interaction. And about 10% show a loss in NLGI grade. So what I'll do next is explain and dig down more into the details of what cases, what grease and polymer combinations. Okay, so in cases of consistency gain, we see this most common in the results with lithium and lithium complex greases. Much like we know about lithium greases, they're very versatile. They work with a lot of different additives very well. Calcium sulfonate, when it gained consistency, there's few cases, it tended to gain the most consistency with very high molecular weight polymers, the tackifiers. We did find in a very interesting case that clay greases increased consistency quite noticeably. And what we assume is happening is you have your clay particle here, and these hydrogen bonding or reactive polymers can help to actually disperse the clay grease, because the clay grease, that thickener, has a lot of hydroxyl groups on the surface. Our polymers that we've added that are hydrogen bonding or reactive, they can couple that hydrogen bonding surface of the silica with the nonpolar base grease. So it's almost a dispersant effect. It helps to disperse the clay thickener better into the base oil, and we see noticeable consistency gain with clay greases and these hydrogen bonding or reactive polymers. In the case of consistency loss, we only saw this with the globular greases, those micellar waxy greases, mostly in the stearate-based aluminum complex grease. This is your aluminum stearate benzoate complex. What we interpret these results as is a wax disruption effect. So here we have our aluminum complex grease, our globules, our micelles are forming waxy stearate interactions, and this is how we form our waxy globular network. When we add the wrong polymer or some of our own waxy polymers, what we interpret these results meaning is that polymer, because it's waxy, interferes or screens the reaction between two globules. So now we've broken that attraction between the stearates by the polymer. So the polymer is inhibiting the waxy globule network from forming. In the remainder of cases, we find that the consistency did not change with the addition of grease polymers. This happened most commonly with silica greases. Our explanation being that silica greases, especially fumed silica, are very inert. Most of the surface functionality has been burnt away in the fuming process. Greases with dispersant polymethacrylates, we didn't see much change in consistency at all. Very low interactions. So that we had thought that maybe dispersant PMAs or polymethacrylates could provide a hydrogen bonding polymer effect, but we didn't see that. I think it's because these long alkyl groups block the polar sites that are very close to the backbone of the polymer. So the grease thickener just can't get into the structure to interact. And last was the greases with the low molecular weight hydrogen bonding polymer. So this polymer was just too insoluble. You need a little bit of solubility for the grease polymer to work, but if it's too insoluble, the grease polymer. Okay, so with roll stability, as I said, all of the cases where we saw positive changes in roll stability, positive changes in grease consistency, we then ran the roll stability. In about half of cases, we saw no change in roll stability. In about a quarter of cases, we saw more stability, so that the grease was more shear stable. And about a quarter of cases, the grease was less shear stable. And again, I'm going to explain each of these three cases in further detail. So roll stability improvement, it occurred mostly in the lithium complex grease. So the trend that we found is if you compare roll stability change versus the grease polymer, the trend seems to follow the highest molecular weight polymers tend to also provide the lowest shear loss. So the higher the molecular weight of the polymer, the higher the shear stability of the grease. This also coincides with increased viscosity. So what we want to do in the future is this increase in roll stability a matter of high molecular weight polymer or a matter of the increased viscosity from that high molecular weight polymer? So we want to further investigate that. We saw roll stability worsen with calcium sulfonate and aluminum complex greases. So in general, those globular greases are very sensitive, and we know that from many years of research. Is that the globular greases, calcium sulfonate, aluminum complex, they are very particular. They're very specific with your grease polymer. Many grease polymers don't work well in these greases. Well, we actually found that roll stability worsened only when we used hydrogen bonding or reactive polymers. So these are actually going to reduce the roll stability of the grease. Our hypothesis here is that when we have the grease and we're taking our cone penetration measurement, we see increased cones, we see increased grade, but when we mix them, we believe that the breaking up of the globules of the micelles allows the polymer to get in between the micelles and screen the interaction. So they kind of, again, it's a waxy wax network disruption effect. So this would explain why we see an increase in NLGI grade with the static cone penetration, but then when we actually put a lot of energy in mixing in and we start to break up that grease, suddenly we see a drastic loss. There is discussion, people have asked, is this from not milling post-addition? But we don't find this effect to be consistent across the board. It doesn't happen for the same polymers or the same greases. So we don't think that there is a post-milling or not post-milling effect. In the last case with roll stability being unaffected, this is most common with the simple lithium and clay greases. So the simpler grease. But we do consider this, even though this kind of an uninteresting or boring effect, there's no change in roll stability, you have to realize that we're getting at least a half or a full NLGI grade, and we're not losing any consistency. So we're getting less consistency from the thickener, we're getting more consistency from the polymer, and we're not losing any roll stability. I consider that to be a win for grease polymers. So we've talked a lot about grease polymers and grease shearing with roll stability. Let's compare that just so we get a sense. Is roll stability an aggressive test? Is cone penetration an aggressive test? Well, when you compare worked cone penetration and roll stability against diesel engine or engine oil, Kurt-Orban shear testing, or hydraulic fluid sonic shear testing, or gear oil KRL testing, if you compare the nominal speeds, the RPMs, the linear, the flow rates, or you compare the loads and pressures applied, compare the temperatures, or you compare the number of hours, lube oil polymers that are very similar to good grease polymers, they can stand up to a lot more aggressive environments than what we're putting on grease with worked cone or roll stability. Roll stability is a loaded test, but there's still 5 kg of load versus we're putting about a short ton of load in KRL. And it's the same, all the polymers are coming from similar chemistries. So I think polymers in general can just hold up to a lot more stresses than what we put through in most grease shear stability tests. So just as a final look at shear stability, what we went ahead and did is compared the weakest shear stability method, Kurt-Orban 30 cycle, this is the D6278. We compared the shear stability index versus an effective shear stability if you took that 1% solution of polymer in 100 neutral oil. If you took that same solution and put that into the cone penetration and ran 100,000 worked cone, what shear stability would it be? Well, we see with 1% polymer and oil, no shear losses at all. So our 25 SSI polymer, this is a very shear stable engine oil polymer. There's no change. But at the same rate, a very shear sensitive polymer, this is too unstable for engine oil, but might work in some applications. Again, we see no change or no loss when we do shear stability index by worked cone. Now, if we make the solution more concentrated, if we make it more like a viscosity improver, thousands of centistokes at even 100 degrees Celsius, we do find about 90% less shear in the cone penetration versus Kurt Orban. So our 25 SSI polymer behaves like a 2 SSI polymer, about 90% less shear loss. Even our 75 SSI polymer, about 90% less shear loss. It acts as a 9 SSI polymer, so essentially very shear stable in the worked cone penetration. So when we talk about polymers and are they shear stable enough for grease, are they inhibiting the performance of grease? I don't think that they are. I think it comes down to interactions like what we've seen with globular greases, where there is some kind of antagonistic waxy disruption. I think when you pick a great grease polymer with a great grease, that you get very. So to summarize, we've talked about a lot of things today, and thank you for your attention. What we find is that grease polymers continue to be a very versatile tool for formulators. They very often provide increases in consistency, and generally that consistency that you're adding does not shear out. It is not compromising the mechanical stability of the grease. What we found very importantly is that different thickeners respond differently to different greases. So this is key. You can't take any grease and add any polymer and expect good results. You always need to tune the interaction between the grease and the grease polymer. We know lithium greases are highly versatile. Calcium and aluminum complex greases are very sensitive. They can lose grade, but they can also gain grade. They're very selective. You need to work very carefully. And particle greases are rather inert, but we do find, interestingly enough, that they do interact with hydrogen bonding and reactive polymers. So there is that dispersant type of effect that I talked about. In the future, so the most important point is that a lot of what I've explained today are essentially qualitative explanations. So this is a high-level study that is meant to serve as a foundation for future work. So my explanations for one thing or another, they need to be validated. But what we find is that our explanations are consistent with the results we're getting, and we can use these qualitative interpretations to predict and guide formulators to make good decisions to make better grease. Improvements, the main improvement I would say is that we need to use a wider range of performance in the starting greases. So I think too many of the initial greases that we used, the base greases, they had really good shear stability to start with. Now that's great for proving out that polymers don't hurt roll stability, because we started with really good roll stability and we maintained really good roll stability. But in the future, to show that grease polymers can continue to improve roll stability, we need more examples like the lithium complex grease that had high roll stability changes. We need more greases like that. Thank you everyone again for your attention and your participation. It's been an honor to present at KSTLE this year, and I hope this work helps you in any current struggles with optimizing polymers and grease, or has served to kind of fulfill any interests you may have on the topic.